So am I audible? Hello, can I can I start? So in last class we started this posterior probability estimation, that is probability omega j given x directly from data. So the method that we saw was k nearest neighbor. In this, what we do is we take the samples given to us and we take x test, that is the sample which is to be classified, and take say a circle around it, say in this case like this, and then we search for k samples. Suppose I search for k equal to 5, then irrespective of what is class of that data sample, we search for closest 5 samples. Okay, then we take a majority call, which class is the major class. So if class of say count of omega 1 is 3 and say count of omega 2 is 2 or so, then we decide that it belongs to omega 1. So it's very simple. So then we saw theoretically how that is actually doing the posterior estimation. So we proved that probability of omega I given x is nothing but ki by k. So ki by k is the probability estimation, it's approximation, right? So that means we will search for k samples around the test sample, and then we will analyze those k neighbors of test sample and check who is having the highest members in that, which class is having highest members in that. So that becomes our decision. So let Dn equal to x1, x2 up to xn be a set of n prototypes. So these are prototypes of different classes. Then let x dash be the closest prototype to a test point x. Then the nearest neighbor rule for classifying x is to assign its label associated with x dash. Okay, so it means if this is your input x, which is to be classified, and this is the x dash, which is the closest sample from your data set. Okay, then take label of this, suppose L1 or Li, and assign it to this. So that is what we are going to do. So this is taking into account only one sample around this x, which is closest. The nearest neighbor rule leads to an error rate greater than the minimum possible base error. So this you can note down. This is simple, but it has error rate more than base. Okay, so base is supposed to be the optimal decision making system with minimum possible error. So this error rate in nearest neighbor is more than base. Okay, so we can prove that for nearest neighbor, the error is actually in the range, say, error of base and maybe twice error of base. With this we can prove. If n is very large, it is reasonable to assume that x dash, that is the prototype, which is close to x, so that probability of omega I given x is approximately equal to probability of omega I given x dash. Okay, so that means if samples are very large and this x which is given to us for testing, then you will find that this x dash, which is the prototype, will be very close to this x. So you can easily assume that label of this is label of x. Okay, so to have better performance of nearest neighbor, you must have large n, that is number of samples. Now this is the boundary creation due to nearest neighbor rule. Suppose I have implemented nearest neighbor rule, then you will find that how partitions are created in space, in feature space. Now this kind of diagram that shows the partition due to prototypes is called as Voronoi tessellation. And for example, suppose this is our problem domain and this is sample say belongs to class 1 and this is sample belonging to class 2. Now suppose I have a test sample here, say x. So if I'm implementing nearest neighbor rule, then I will find out this distance say d1 and this distance d2. Then I will say d2 is less than d1, so whatever is this orange label will be the label of this x. Similarly, suppose my x test is here, then I just take this distance d1 and this distance as d2. So d1 is less than d2. So the label assigned to this will be blue. So if I keep on doing like this for all the samples in the square domain, where will be the boundary between two classes? So this will be the boundary between two classes. So if you take any sample, suppose I take sample here, then distance from this to say class 1 to x and class 2 to x is same. So d1 is equal to d2. This will happen on this line. Okay, so you take any sample on this line, d1 is equal to d2, so you cannot decide label for that sample. So such kind of a line where you cannot take the decision where d1 is equal to d2 is called as decision boundary between two classes. Now this side of this line now is class say 2 and this side becomes class 1 or red class and orange class. So by just implementing nearest neighbor rule, we have created this decision boundary. Okay, so when I implement nearest neighbor, That means we are implementing this decision line between these two classes. Now we will go further. I add now one more sample. So this is one more sample due to say, or this belongs to blue class. Now if I add this, what will be the new boundary? Now if I add this, we'll see that a new boundary is created like this, and that will be the boundary between two classes. So this side is class 2 and this side is class 1. Okay. So this new zone is formed due to this additional prototype. If this was not there, then we have only one boundary. Now if I keep on adding like this, so if I add one more sample here, which belongs to again class 1, then where this boundary will come. So this boundary will come. You can see I am joining actually these two and passing a line which is perpendicular to this. So every time I add one sample, one prototype, there will be a zone formation, a new zone formation for respective class. So this will be complete zone belongs to class 1. So whatever, if anybody, any sample falls in that zone will be classified as class 1. So this complete zone is again class 1. Okay. So such diagram is called as Voronoi tessellation, and this zone is class 2. So any sample, any test sample falling in this area is belonging to class 2. If I add one more orange sample, see what happens. So I have to change the cell. So this will be now cell representing class 2. Okay. So if I add one more, then this will be also zone for class 2. And obviously this will be class 1. So like that, by implementing a nearest neighbor rule, you can see that we are actually creating non-linear boundaries. So this is a zone actually. Uh, so if I do it properly, so this is a zone which belongs to class 1, and this zone which is class 2 is actually submerged in this class 1 zone. Okay, so this is a non-linear boundary implementation. Now you can see if I take more samples, so like this, say this gray area is class say 1 and white area is class 2. So you can see that we can create very complicated boundaries with the help of KNN. So KNN is a very powerful algorithm. So this is a 2D example and this is a 3D example. So you can read more on this in Duda's book. So that is available. Now this metrics plays an important role in KNN. Metric means the way of measuring distance between two classes or two samples actually. So this is X and this is suppose X2 and X1. The distance between these two is measured generally using Euclidean norm, but there are other ways of doing this. So what are the other ways of doing this that we will see? And depending on the problem, you may change the ways of measuring in your problem. Now a metric must have four properties so that you can use it in your problem. The measurement, distance measurement method must return you a positive number or equal to at the most 0. Okay, distance cannot be negative between 2 points. Suppose this is point A and this is B. This distance AB must be greater than 0. It cannot be less than 0. The next property it should follow is reflexivity. That means distance AB is equal to 0 if A is equal to B. So the distance between the same point, that is A with A, is 0. That must be followed. The next point is symmetry. So if I take say A here and B here, so distance AB must be equal to distance BA. Okay, so if that is the case, then you can use that function as distance function. The fourth one is triangular inequality, that means distance between AB divided by distance between BC must be greater than distance between A and C at the most equal. So generally we have equal, but if it is more than that, that is also allowed. So this is adding some flexibility. So to use any function as a distance matrix function, these four properties must be followed. So based on that, we have a generalized distance metric called as Minkowski distance norm or LK norm. So which is given by say distance LK between A and B is equal to kth root of summation I equal to 1 to B. It's absolute value of AI minus BI. So if this is the case, then it is called as generalized distance norm or LK norm or Minkowski norm. Now if you put different values of K, you will get different norms which are popular. Now suppose I put K equal to 1 in this equation, then it is called as city block distance or L1 norm. So L1 norm is given by, so put K equal to 1 here. So it will be just a summation I equal to 1 to B, absolute value of this difference AI minus BI. Okay. Now if you put K equal to 2, then it becomes Euclidean norm, which is quite popular and you are aware of. So it is just A minus B square and square root of that. So you may be aware with this equation. Say distance between x1 and say x2 is a distance between 2 points, that is x1, y1 and x2, y2. So this is normally known to everybody. So that is actually L2 norm. Now for various values of k, if you plot this, so this is your point, suppose A, and on this curve you take another point B, and distance between them if you measure with k equal to zero point 0.5. So this is a unit distance between 2 points, okay, with k equal to 0.5. If you take k equal to 1, then the distance between all these points is same. It may not look same to you, but actually it is same with k equal to 1. Here also this distance as per k equal to 0.5. So if you take k equal to 2, that is Euclidean norm, then immediately you will agree that this distance is same. Okay, so it will be a circular kind of a thing. You take distance from this A to any point B on this circumference is actually the radius of the circle, and the distance is say y or unit. Now here if you take k equal to 4, these distances are same. If you take k equal to infinite, if you take k equal to infinite, then this will be the structure. So once you change the distance norm, you get actually different results in your KNN. So KNN is very sensitive how you measure distance between 2 points. So it's not always a good idea to use this Euclidean in all the problems. You may use say city block distance or Manhattan distance kind of thing, or say L infinite or L2 is normal, L1. So you have to try all these norms based on your experience, which gives you good results that you can keep. Now, there are always some disadvantages when you have some benefits. So when you take KNN, we have to think about the computational complexity of KNN. So when you take any point, say this X and this prototype, say XI, we have to measure distance. Now, distance measurement, if this point, so we should write here capital D so that this will be good. So the distance between 2 points is suppose D, and these 2 points are d-dimensional. Then you can see here, if it is two-dimensional, we have to do this two computations. If it is d-dimensional, we have to do d computations. So the complexity is big O B if it is the distance calculation between 2 points. Now, if we have such n prototypes, then we have to repeat this for all n samples. That means for each sample we have d calculations. Then for n samples, that is total number of prototypes, we have to do dn calculations. So it's growing very fast when samples are increasing and dimensions are increasing. So to reduce the complexity, we can have three approaches. Computing partial distance, so don't use all the dimensions given to you. You can have suppose 10 dimensions, then you may choose 5 dimensions for measurement. So those dimensions may be the dominant dimensions. So that is possible. Uh, so it is called as partial distance measurement. Now, second approach is create a search tree in which prototypes are selectively linked. Okay, so we can form uh, some relation between the prototypes, and then we can avoid calculation of distances every time. Then the third approach is eliminate useless prototypes. So we know that there are some prototypes that you can easily eliminate from your list. Still, there won't be any problem. Say, for example, I have 100 samples per class for 10 classes, so total 1000 samples. But I find that, okay, if I take only 10 samples per class, still my results are not deteriorating. So I can use 10 samples per class. So instead of 1000 samples, I can reduce computation by just considering 100 samples. So that is all other way of doing or reducing the complexity. Now consider a problem where we are now implementing KNN. Now this is a data given to us, and question is classify sample 3 using KNN. So this is a list you can plot here. So the scatter plot is like this. So 5 samples here and 7 here and so on. So there are 3 classes like this. And question is find out the class for 3 2. So 3 is here and 2 is here. So your X test is lying here. So question is to which class it belongs. Now first of all we will do the distance calculation. So from the given point, that is 3 2. So this is 3 2. We will find out distance with everybody. So that is our first task. So whatever samples are given to us as training prototypes. So these are all prototypes. So this is our feature x1 and x2. So one sample here means this thing. This belongs to class 3. The second sample is here belongs to class 2 and so on. So this was the list. Few samples belongs to class 1, then few samples belongs to class 2 and few go to class 3. So what I do, I take this sample 3 2 and find out distance with everybody. And then I sort it. So this is the sorted version of the distance, say from minimum distance to maximum that I am considering. Okay, so this is now ordered in that way. So don't forget to write proper labels for each class, so that you have to maintain. So 0.8 was belonging to class 1, so write proper label in this column. But you have to sort this as per distance. So this is the farthest point from 3 2. Now this is the closest one. So if k equal to 1, if I consider k equal to 1, that means I will consider only nearest sample. Then label of that is 3. So I can take a decision that 3 2 belongs to omega 3. Now instead of that, suppose I take k equal to 3. That means I will take 3 nearest neighbors to take a decision. Then I take that sorted list and consider 3 closest samples. Now these are 3 closest samples. So omega 3, there are 2 samples. So this one and this one. Omega 2, there is only one sample. And for omega 0, omega 1, there is no sample. So for k equal to 1 and the maximum is this. So my decision based on k equal to 3 is omega 3. Now if you compare with k equal to 1 and k equal to 3, advantage of taking more neighbors is that you will get theoretically a stable result, because it so happens many times that the nearest sample is a noise. Okay, suppose this is uh, class 1, so this is x, this is omega 1 sample, this is also omega 1, this is omega 1, but by chance this is omega 2, which is very close. So if you take k equal to 1, you have to declare that this is omega 2 sample, then you can get a better idea. Now next is called a modified KNN. Instead of using simple majority rule, modified KNN employs a weighted majority rule. So this reduces efforts of outlier patterns. Now how much close prototypes are plays an important role in. I will tell you how it is implemented. Here what we do, so instead of taking distances, we take a decision of the prototype. This is some omega j equal to d max minus dj. So jth prototype is with what we do, we take from the, say this is x, and we are finding out distances with all the prototypes which are given to us, say from x1 supposed to xn. And let us say this is some xj sample. So distance with that is dj, this is d1, maybe some dk, and this is dn. So we are now talking about these two. I want to find out importance of this sample for classifying this sample. So that I will call it as Wj or weight. Now what we have to do, we have to first of all find out distance of this test sample with everybody. So we have say n distances from d1 to dn. So out of that, first of all, you find out maximum distance and minimum distance. Okay, so then the weight Wj is given by this thing. So for a jth prototype, you take max distance minus dj, the distance for j prototype, divided by d max minus d min. Okay, and if dj happens to be the minimum, then you just write their importance as 1. So by doing so, what happens is, if you are the most distant pattern, this importance to you is 0, and if you are the closest pattern, then importance is 1. So this wj varies in the range 0 to 1. I will take one example. Consider the following data similar to earlier data. We have the same sample 3, 2, and we have to use say modified KNN here. So what is first step? First step is same, find out all distances. So what I have done, I have calculated distances with each these prototypes with respect to test sample 3, 2. Okay, so these are our prototypes belonging to different classes. Now I calculate the distance and then I sort from minimum to maximum. Okay. So this is the minimum distance and this is the maximum distance. So this is d min for our formula of weight, and this is d max. So here we are considering say k equal to 5 only. So only 5 neighbors will be taken into account. So first 5 closest neighbors we take into account and compute their importance. So importance is here. So since this is the closest one, its importance is 1. Okay. And with our formula, that is d max minus dj upon d max minus d sorry d max minus d min. So with this, I calculated all this. Okay, so once I do that, I make another table here for each class, say omegas 1, omega 2, and omega 3. Since I don't have any sample here which belongs to omega 1, I put straight away 0 here. Now out of the 5 that we have selected, this sample, third sample, belongs to omega 3. So I put its importance in this column of omega 3. This second pattern belongs to omega 2. So I put its importance here. Then the third one belongs to omega 3. So I put here. And for the second, this fourth sample, it belongs to omega 2 and its importance is 0. So that I have. So everybody is now placed in proper position. So next step is to add the total weightage. So this weightage is 0, this is 0.9655, and this is 1.31. So here k was 5 and I got highest importance to omega 3. So my decision is omega 3. Now suppose instead of k equal to 5, I made it k equal to 7. So what we have to do, we have to take same table, previous table, and we have to include now these two things, these two samples which are closest. So they will fall in closest 7 sample list. So that I'm taking now. And then using this formula for Wj, I computed importance for each sample. So now we have to compute it for 7 samples. Then you shift the importance to this table for omega 1, omega 2 and omega 3 and add importance or weightages of respective classes. Now here you will get 1.65 for omega 3 and 1.4 for omega 2. I think I have changed here the pattern. No? Earlier it was 3.2 in previous problem. Now this is 4.2 and 1.8. Okay, so here the pattern is changed to 4.2 and 1.8. Okay, still the decision is, I think it should be omega 3 here because it is producing largest. So like that we can use the modified KNN or KNN to get the decisions. Here remember we are doing the prediction of omega I given X directly. We need not use Bayes here, Bayes rule to compute this. We estimated this directly, and to take decision we are using Bayes rule. So we will go with Bayes rule, but we will not calculate likelihood and or estimate likelihood and then compute posterior. So that step is avoided. So that's why this is very popular. Okay. So there are various versions of KNNs you will find, and all the packages will support this KNN method directly. So in Python you will get different packages and you will see that these commands are implemented maybe in 1 or 2 lines. Okay, so if you have any doubt you can ask, otherwise we will start.